All right, let's talk about the physics of flight. I mean, we're talking about everything from a home run soaring out of the park to a satellite orbiting the Earth to even just a single drop of rain. We're going to break down projectile motion, these kind of universal rules that control literally anything that's flying through the air under the pull of gravity.
You ever wonder about that? Like how a video game character times that jump just right, or how a quarterback throws a perfect spiral? Well, the answer is physics. That beautiful arc of a basketball shot and the path of a rocket, they actually share the same invisible blueprint. And that blueprint? That's projectile motion. We're about to unpack it.
Okay, so first things first. Before we can understand how projectiles move, we gotta have a really clear idea of what a projectile even is. Now, the absolute key to this definition is that last part, only acted upon by the force of gravity. This is our starting point, our foundational rule. For this perfect, ideal model we're building, we're going to ignore all the messy stuff for a minute. You know, things like air resistance or engine power. It's just the object and gravity, locked in this pure, predictable dance. So to get started, we're going to simplify things a lot. We're going to look at the world in 2 dimensions. I want you to think of it kind of like an old-school side-scrolling video game. There's only up, down, left, and right. That's it.
Okay, this right here, this is the single most important thing to understand about projectile motion. It's the big secret. The horizontal movement and the vertical movement are completely 100% independent. What the object is doing sideways has absolutely zero effect on what it's doing up and down. They're like 2 separate stories happening at the exact same time.
To really get this, imagine a little experiment. Let's say you drop one ball straight down. At the exact same moment, you fire another ball perfectly horizontally. Guess what? They both hit the ground at the exact same time. Why? Because gravity's downward pull doesn't care about sideways speed. It pulls them down at the same rate. So that horizontal motion just keeps cruising along at a steady speed, while the vertical motion is in this constant battle with gravity.
So when you put those 2 independent motions together, you get that classic, beautiful parabolic arc. At launch, the object has speed going both forward and up. As it climbs, gravity is constantly slowing down that upward speed until, for just a split second, it hits 0 at the very peak. And the whole time, its forward speed hasn't changed at all. Then, gravity wins the tug of war and starts pulling it back down, accelerating it toward the ground.
All right, so we've totally mastered the flat world. But, you know, reality isn't a 2D video game, right? It's time to add some depth. It's time to bring our model into the 3rd dimension.
We've been working on a simple graph, with an x-axis for left and right and a y-axis for up and down. And it's a perfect way to learn the basics, but it just can't explain everything we see out there in the real world.
But now, we add just one more axis, the z-axis. This gives us depth. This takes our nice flat parabola and lets it move in any direction through 3-dimensional space. And just like that, the possibilities for how something can move just exploded.
So what does this actually mean? Well, it means we can finally explain things like the Magnus effect that makes a curveball, curve. We can model the amazing stability of a quarterback's spiral pass or figure out the complex flight path of a drone. The z-axis is what makes our physics model really, truly match the world we live in.
Okay, so this is all really cool in theory, but how does it actually get used? Let's connect these physics ideas to some real-world stuff that athletes and engineers are thinking about every single day.
This chart right here shows us something incredibly useful, the best angle to launch something if you want it to go as far as possible. So why is 45 degrees the magic number? Well, it's the perfect trade-off. See, if you launch at a low angle, you get a lot of forward speed, but not much hang time. If you launch really high, you get tons of time in the air, but you don't go very far forward. 45 degrees is that perfect sweet spot that balances your time in the air with your forward speed to give you the maximum possible distance.
Phew, we have gone on quite a journey, from a simple 2D arc all the way to the wild complexities of 3D motion. So let's just quickly recap the biggest takeaways here. So if you remember anything, remember this. 1. Our whole model starts with an ideal projectile, where gravity is the only thing in charge. 2. The absolute game changer is knowing that horizontal and vertical motions are separate things. They don't affect each other. And 3. Adding that 3rd dimension, the z-axis, is what lets us model all the cool, complicated stuff we see in real life, like spin and curve.
And that leaves us with one final thought. Everything we've talked about works perfectly in a vacuum, with no air. But we all know from experience that a feather and a bowling ball do not fall the same way in the real world. So when you start adding in forces like air resistance, well, that's where the next level of physics really begins. How does that one extra force change everything we've just learned? Now that's something to think about.